Hilder Math 126 fans here. We're going to derive the center of mass for a thin plate. This actually generalizes something we do in Math 125, but the presentation is just better in this setting since we know how to describe regions. So assume we have a region. Assume we've placed it kind of in a grid here. And then assume we have a formula, xy, rho of xy, which is the density at xy. And what we really mean by that is if you cut out a little square here, what's its mass? Mass per unit area. It's actually a limiting density as it gets smaller and smaller. So it's the density. So just think of this as if you cut out a little 1 by 1 square, what's its density? Now we're going to assume it doesn't have to be constant. In Math 125 it had to be constant, but in this course it can be anything. So we can have it be heavier if you go this way, or lighter. We can have it be heavier as you go out. Okay. The goal here is to find the center of mass. Now we already know from my, watch our previous video on balancing on a seesaw, how to balance two people this way and this way, like if you had a point here and a point here. And that was this formula that x bar is m1x1 plus m2x2, and you keep going until you do all the points, divided by the total mass of the system. So that all started with this little discussion of the seesaw. It turns out that if you're doing something in 3D, you can do the same thing, and then you just also do it for y. How do things balance this way? So this is y bar is m1 y1 plus mn yn divided by the sums of the masses. And you don't have to know the derivation here to use it. So if you don't want to know why, just skip straight to the homework. But this is giving a little bit of why. Okay, so the idea is this, and this is the way we use calculus, is we break it into a bunch of small pieces, and then we ask ourselves, let's pretend that that's 1 point, like one person. Let's pretend this is one person. Let's pretend this is one person. And then we're going to use our formulas. So if I just grab one out of the middle, which is what this is saying, the reason it's using an I and a J is because you would have like I equals 1 would be the first row, and then I equals 2, and then I equals 3, and then I equals 4. So maybe this would be like I equals 7, the 7th column. And then you might have, when I'm here, maybe it's the 3rd row. So that's what this notation is saying. Assume that x of I, j is the x value in the 7th row in the 3rd column. That's what that's saying. And you have a similar y value in each one. So let's assume we take the center of each point as a point. And that's what we're going to plug in here into these spots. So it's actually a double sum. We're going to be plugging in all the x's for each row and each column into this thing. It's a huge mess here. So we're going to have something that looks like x11 plus x12. You'll run through all the possible x's, and you'll eventually finish with x and n, the very last point in the corner, assuming it's sort of a square thing. But the thing we don't know is the masses. What's the mass there? What's the mass at the next point? And so the strategy is this. We are just going to, when we get to this point, we're going to pretend that all of the mass at that one point is there. So we are going to find the mass of one box. And that's what we're going to put here. The mass of the box that's around that point. And then the mass of the box. And then we're going to do the same, whatever that number we get there, we're going to put here as well. So this is a cleaner derivation if you compare it with the 125 derivation, because we can do both the same way. So the question becomes, what is the mass of one box? Well, the width of the box is what we are going to call delta x, how wide it is this way, and the height is going to be delta y. And it's fairly simple. If this is the density, so by density we mean something like kilograms per square meter, and this is the x and y, what is the area? So ultimately the mass at a given row and a given column, I know there's a lot of notation there, is the density at that x value, whatever it is, times the area on the ground, or dx dy, or dy dx, that thing. That's what we're going to put in all of these spots, the corresponding value. And that's our answer. So the reason I am saying that is that gives us the following. So then it's going to be a big sum, and I think I'll use some sum notation. So it's going to be the sum over each row, meaning we're going to add up all the values there, and over each column. And then we are going to do this. This is the mass. The mass is going to be the density times the area of the base times the x value. And then when we're done, we're going to divide by this double sum of the density times the area of the base. A lot of notation, a lot of stuff all coming together. We call the thing on top the moment. We actually call this the moment about the y-axis, which confuses everybody because we're using x's, but it's how the mass is distributed around the y-axis. It's a physics term. And this is called the total mass on the bottom. Okay, if you then take the limit as m and n go to infinity, this looks like an integral. This is like dA. And that's where our formula comes from. So we say x bar is the double integral over the region of x times the density dA. And that's x. That's where that x is coming from. And then the bottom is the total mass. And that's it. And then you can do the exact same thing for y bar. This is where I say the derivation is nicer here, because in Math 125, we had to get everything in terms of x or in terms of y, but because we have double integrals, we can do everything directly with the double integral notation. So that's it. It gives you the real goal here is to give our students a chance to see something else we use double integrals for. Here it's being used to add up mass times x or mass times y. All right, that's the derivation.